This Project Ocean remote lesson is on water column structure. This is going to be one of the longer and more complicated remote lessons that you'll cover in the Project Ocean course. This is where we start to put it all together and start to look at the stability of the ocean water column. So let's jump right into it. As usual, you can see your learning objectives, and please review this against your Project Ocean understandings that you can find on D2L. There's quite a few of them here. A total of 15 different learning objectives. Before we jump into talking about water column structure, we need to start with some definitions. You're going to hear me use the term parcel of seawater when I talk about physical oceanography. A parcel is defined as a unit volume of seawater with uniform properties. We constrain that volume in Cartesian space as a unit change in the x direction, which in physical oceanography is defined as increasing positive in the eastward direction, the y direction, which is defined in physical oceanography as increasing positive in the northward direction, and the z direction. Now this is very important in physical oceanography. The z direction is defined as increasing positive up into the atmosphere. In other words, from the ocean surface positive into the atmosphere. That means as we go deeper in the ocean, z becomes increasingly more negative. Pay attention to that as we go through. That's going to be different from the term depth. Now, in addition to our unit lengths, x, y, and z, in Cartesian space, we define velocity in the x direction as u, velocity in the y direction as v, and velocity in the z direction as w. We'll get to that later when we talk about physical circulation. Our next definition is the term water column. Again, you may have heard me say that already in your remote lessons. Let's define it. A water column is a fixed area of seawater extending from the ocean surface to the seafloor. Again, pay attention here. Z is increasing negative the deeper you go into the ocean. Do not confuse that with depth. Depth is going to be increasing positive the deeper you go. For example, a depth of 1,000 meters is positive 1,000 meters. That would be negative 1,000 meters z. And the last definition we have to look at is a definition of what's called a water mass. Water mass are bodies of water with fairly uniform characteristics, mainly temperature and salinity, that have distinct sources in particular regions or areas of the ocean. We're going to revisit water mass a lot when we talk about density-driven flows in the ocean, or what we call thermohaline circulation. Speaking of density, I told you you'd see it again. Here it is. We're going to come back to density over and over and over again. In fact, in this remote lesson, we're going to talk a lot about density. Mathematically, again, density is mass over volume. Be careful to not confuse density with weight. For fluids like seawater, let's think of density as how tightly the molecules of a substance are packed together. In other words, let's use the terms more dense versus less dense. Now, I'll get right to the punchline. When we're talking about seawater, the things that affect density are salinity, temperature, and pressure. And that's what we're going to spend the majority of our time talking about here in this remote lesson. Why? Well, what we'll see is stability is enhanced when density increases with depth. We're going to see stability is going to be a function of stratification. I'll define that in a little bit. Looking at pressure and density. In order to understand pressure, let's start with the hydrostatic equation. Now, the hydrostatic equation states that pressure, or P, is equal to the density of the fluid over it times the gravitational acceleration constant times the depth in the water column expressed as z. Now, you can also apply this same hydrostatic equation to the atmosphere, but let's focus on the water. Notice once again there's a negative sign here. That's to compensate for the fact that z is increasing negative at deeper you go in the ocean. Now, the hydrostatic equation is for an incompressible fluid. Seawater is actually slightly compressible. This is going to become very important when we start talking about the combined effects of pressure, salinity, and temperature on seawater density. But for now, let's look at pressure isolated by itself and just look at the pressure effects on density. Now in the ocean, the downward force of gravity acting on the ocean and the atmospheric column is generally balanced by the upward pressure gradient force. This is what we call hydrostatic balance. If it wasn't balanced, that would mean water would move vertically in the water column. For a seawater parcel of fixed volume, it's pretty simple. As depth increases, z becomes more negative, pressure goes up. Therefore, molecules become more densely packed. Therefore, density goes up. Now, pressure is actually the dominant feature that drives density in a deep ocean water column, but it's less of a factor for the variability of density in shallow waters. We'll see that in a second. But pressure, obviously, is going to change density of a water parcel. Let's look at this graphically. So looking at this diagram, I'm going to be giving you two different water columns, water column A and water column B. Within these water columns, there is a parcel. Now, the parcel in A is at a shallower depth than the parcel in B. So let's look what happens to density. Just as a quick note, we can estimate pressure as being roughly equal to minus 10 to the fourth times z. Again, look at that minus sign because of the notation of z. So this tells us for each meter of depth, we get 10 to the fourth pascals increase in pressure. Now, moving on beyond that thought, let's go back to our original task here and look at the difference in the density between the parcel in column A and the parcel in column B. So the depth of the parcel in water column A is less than the depth of the parcel in water column B. Therefore, the pressure on the parcel in water column A is less than the pressure on the parcel in water column B. Therefore, the density of the parcel in water column A is less than the density of the parcel in water column B. Really simple, right? Well, one of the biggest rules in oceanography is whenever anybody tells you it's simple or easy, it's actually a little more complicated. So remember that I told you that the hydrostatic equation is for an incompressible fluid. Well, seawater is actually slightly compressible. And what we're going to talk about here in this remote lesson is increasing salinity decreases compressibility, and pressure can also affect temperature. So although we're going to look at pressure, salinity, and temperature and their effects on density individually, one by one, remember it's going to be a combined effect of these three seawater properties that are going to affect density. We'll get to that. Let's move on to salinity and density. For a seawater parcel of fixed volume with constant temperature and pressure, as salinity goes up, molecular spacing in the parcel goes down, and more dense ions displace less dense water molecules. Therefore, density goes up. Let me show you what I mean. Here we have a parcel of the same volume, but in parcel A, it's freshwater. In parcel B, it's saltwater. Now, what I did right here is I showed you the gram molecular weight for water, the weight for a sodium ion, and a chloride ion. Let's take for fact, since parcel A is only freshwater, the salinity of parcel A is less than the salinity of parcel B. So if we look at these two parcels and we compare the total weight within the parcels, we have 20 water molecules in parcel A at a weight of 18.02 per each water molecule, which gives us a total of 360.4 atomic mass units. In parcel B, I displaced 3 water molecules with 3 sodium chloride molecules, which dissociate into a sodium ion and a chloride ion. So now if I add this up, I have 17 molecules of water at 18.02 atomic mass units per molecule of water. I have 3 sodium ions at 22.99 atomic mass units per sodium ion, and 3 chloride ions at 35.45 atomic mass units per chloride ion. That gives us a grand total of 481.66 atomic mass units in parcel B. So comparing the masses within the two parcels, it's pretty clear I have a higher mass in parcel B than I do in parcel A, even though the volumes of those parcels are the same. Therefore, the density in parcel A is less than the density in parcel B. Now remember, there's two effects of salinity on density. It's not just the added mass because of more dense ions displacing less dense water molecules. It's also when you add these dissolved ions, it changes molecular spacing. If you look at parcel A and you start to look at the open spaces, what you start to find is in parcel B, there's fewer open spaces. In other words, the molecules are more tightly packed. So those two effects together tells us that as salinity increases in a water parcel, density increases. Looking at the effects of temperature and density, let's once again take two parcels of equal volume, but in each one of these parcels we'll make the temperature different. So parcel A, let's make the temperature lower than parcel B. So for a seawater parcel of fixed volume with constant salinity and pressure, once we increase the heat content, the temperature within the parcel goes up. Therefore, the molecular kinetic energy, which is vibrational and rotational energy within the parcel, also goes up. This is going to increase the molecular spacing and therefore decrease the density within the parcel. Let's look at this graphically. So I have those two parcels with different temperatures. Temperature A lower than temperature B. You can see in parcel B, there's more vibrational and rotational kinetic energy, and there's a larger degree of molecular spacing between the molecules. Therefore, the density within parcel B is less than the density within parcel A. So as temperature goes up, density within the parcel goes down. But remember, we talked about pressure effects on temperature as well. Seawater is slightly compressible. So for a given seawater parcel, if pressure increases with no exchange of heat with surrounding waters, or what we call adiabatically, temperature goes up slightly, and therefore density goes down. And conversely, if pressure goes down adiabatically, temperature within the parcel goes down and density goes up slightly. So you can see that that change in density due to the change in temperature with pressure is acting contrary to the change in density due to pressure alone. So that means when we try to compare water masses, we need to correct for this compressibility effect on temperature. So temperature of seawater is often expressed as potential temperature. This is the temperature a water parcel would have if it was moved adiabatically from one pressure to another reference pressure. The reference pressure typically used is surface pressure, or pressure at the surface of the ocean. Putting it all together, in other words, the combined effects of temperature, salinity, and pressure gets us something called the equation of state for seawater. Now, the actual equation for state for seawater is a pretty long and complicated equation. I'm not going to show you that in the Project Ocean course. What I want you to know is density of seawater is a nonlinear function of temperature, salinity, and pressure. When I say nonlinear, that means that the density change of a seawater parcel for a given change in temperature, salinity, and/or pressure can be different for parcels that have equal density, but start off at different temperature, salinities, and pressures. Now, in the field of oceanography, seawater density is expressed in multiple ways. The first is pretty simple. We just look at temperature, salinity, and pressure and express what the density is. We calculate that with the equation for state. Now, oceanographers usually reference this to the density of pure water, which is 1,000 kilograms per meter cubed. So for example, at a seawater density of 1,025 kilograms per meter cubed, density would be expressed as 1,025 minus 1,000 kilograms per meter cubed equals 25 kilograms per meter cubed. It's just a shorthand way for oceanographers to express density. Density is also expressed as what's called in situ density. So this is density reference to pure water and a reference pressure, usually at the ocean surface. You can see right here that 0 replacing the pressure, and again corrected to pure water. Now the reason this is used, this allows the comparison of water at different depths. And lastly, oceanographers most often use what's called potential density. This is density referenced again to pure water, the potential temperature, and a reference pressure. This is how we're going to trace water masses, because this is going to allow us to compare water parcels at different depths in the world's oceans and look at their properties to trace water masses. We'll get to that when we look at some thermal haline circulation and some surface ocean circulation. Now, in general, seawater density is primarily a function of pressure, especially at depths of 1,000 meters. Kind of makes sense, right? Remember that the ocean water column on average is 3,700 meters deep, but variations in temperature and salinity cause the biggest differences in seawater density in waters less than 1,000 meters. So it's kind of confusing when you hear that. What I'm trying to say here is the ocean water column as a whole, its structure is controlled by increasing pressure with depth. But we'll see that circulation of water and changes in what we call and we'll call stratification in surface water is largely controlled by temperature and salinity. Now, once again, the use of potential density allows us to look at these temperature and salinity effects and trace water parcels and water masses throughout the ocean. Another simplification that oceanographers sometimes use to look at the effects of temperature and salinity on density is it's a linear approximation to the equation of state for seawater. Now, the linear approximation to the equation of state for seawater uses a condition-specific thermal expansion coefficient. That's going to be this alpha T right here, and a condition-specific haline contraction coefficient. In other words, when I see haline, that's halide, that's salt, we're looking at the effects on density due to thermal expansion as one increases temperature, and the effect on density as we add salt and increase density. Now, these two constants, when it says that they're condition specific, means we reference them to an initial state, which is a density of 1,025 kilograms per meter cubed, a salinity of 35, and a temperature of 10 degrees Celsius. Using these values and these constant values for the thermal expansion coefficient and the haline contraction coefficient, we can easily calculate or estimate a change in density of seawater for shallow waters less than 1,000 meters. Now, the reason I show you this is not to have you use this and do mathematical calculations, but looking and comparing the thermal expansion coefficient tells us a lot about the effects of temperature and salinity on density. So the haline contraction coefficient tells us that for every unit change in salinity, I get a 0.78 increase in density of seawater. The thermal expansion coefficient for temperature tells us for every unit increase in temperature in degrees Celsius, I get a 0.15 kilogram per meter cubed decrease in density. Why is it a decrease there? Well, look at that negative sign. So comparing these two coefficients, it tells us that each unit change in salinity has a greater effect on density than each unit change in temperature. Now, that leads us to a really interesting finding. It's pretty clear that salinity has a greater influence on density per unit change in most open ocean waters, less than 1 kilometer deep. But we'll see that temperature is what actually controls ocean structure. Now I'll jump right to it and tell you the reason why, and then I'll show you the reason why. The reason why is, well, the range of change in salinity in deep ocean waters is pretty narrow. It's between 33 to about 37 on average. In fact, salinity in most places on average is 34.5 to 35. So although each unit change in salinity can have a large effect on density, salinity just doesn't change that much. Temperature can vary over a very wide range. We'll see that deep waters in the ocean typically are between 2 to 4 degrees Celsius. Surface waters can be a lot warmer than that. On average globally, they're going to be somewhere between 13 to 15 degrees Celsius. So that's a very wide range in temperature change. So although each unit change in temperature has a smaller effect on density, temperature varies over a much wider range, and therefore we'll see temperature is what's really going to control density structure in the upper ocean. Be careful here. That's not the case for estuaries like Chesapeake Bay, where salinity can change because seawater mixes with freshwater, and we'll see it's not necessarily the cases for the Arctic Ocean basin. Remember when we talked about the Arctic Ocean basin, we talked about some freshwater effects due to multi-year ice, land ice, and rivers that empty into that ocean surrounded by land. So in many ways, the Arctic Ocean is kind of like a big estuary. Hold that thought and we'll get to it when we talk about Arctic Ocean circulation. Well, I already kind of mentioned this. Here's a nice plot of global surface ocean salinity. This is showing you the decadal average surface ocean salinity from 1955 to 2017, and this is from the World Ocean Atlas Climatology. Now you can see just by looking at it, there are variations in salinity throughout a surface ocean. But if we look at our axis right here, or I should say our legend scale, we can see that that's a pretty narrow range from as low as 31 to as high as 36 plus. And really, for the majority of the ocean, the range is even tighter from about, well, really about 33 up to about 36. With the exception, remember, the Arctic Ocean is a fresher ocean basin than the other ocean basins due to those effects we've already talked about. So ocean salinity in surface waters typically varies over a relatively small range of about 33 to 37. I already stated this, I'll state it again. On average, ocean salinity is approximately between 34.5 and 35. So not a lot of variability in ocean salinity. Where you do see variability, it's going to be linked to changes in evaporation and precipitation or proximity to freshwater sources like river mouths, or in the case of the Arctic Ocean, areas where we have inputs from land ice, multi-year ice, or rivers. Now that we've looked at the factors that affect surface water salinity, we can take a look at a typical generalized ocean water column profile for salinity. Now, when I say typical generalized, we can see different profiles at different points of the ocean, but based on the general principles we just covered, this is the type of profile one would expect if one was measuring salinity in the deep ocean. As with all things oceanography, we need some definitions. So a zone where salinity decreases or increases with depth is called a halocline. Whenever you see that suffix cline, that means a change in something with depth. In the case of a halocline, halo is halide, and cline is a change in something with depth. So a halocline is a change in salt with depth, or a change in salinity with depth. Now in the deep ocean, surface salinity and the slope of the halocline is determined by a balance between precipitation and evaporation at the surface. Let's start at the surface. So you see right here in the upper 200 meters of an ocean water column is an area we call the surface mix layer. The surface mix layer is a zone that's continuously mixed by wind and wave action at the surface. Now the 200 meter cutoff is an average depth for the surface mix layer in the ocean. Sometimes it could be a little deeper, sometimes it could be a little shallower. It's characterized by relatively uniform properties of seawater within that layer because it's continuously mixed. Now compare the salinity in this case in that surface mix layer, which is somewhere about 36.25, to the salinity here in the deeper waters. The deeper waters have a salinity in the world's oceans somewhere between about 34.5 to 35. Salinity is very stable in deeper waters, greater than 1,000 or greater than 1,500 meters in depth. So the difference between these salinities drives a halocline. Remember that halocline is going to be a zone where salinities are increasing or decreasing with depth. In the case of this blue line, we can see a halocline That's the balance or the diffusive balance of salt between the surface mixed layer and deep waters. Now, once again, notice this is a pretty narrow range in salinity that we're talking about. So be careful when you look at salinity profiles. They're often exaggerated to show structure, when the structure in deep oceans not that extreme. The other case I show you right here is a case where surface mixed layer salinity is less than the deep water. That would be a case where we have a higher rate of precipitation than evaporation, and it follows that the halocline would be increasing with depth. We'll take a better look at salinity distributions in ocean basins when we get into density-driven circulation. For now, I want you to know that lines of equal salinity are what we call isohalines. We can use this to trace different water masses in ocean basins. But still, even looking at this vertical cross-section showing the distribution of salinity with depth in the Western Atlantic, in other words, this is up by the Arctic, this is down by Antarctica, one can see that salinity only varies at a small range from about 34.8 to about 36.5 in the Atlantic basin. So we'll get to this later, but realize salinity is one of the ways we're going to trace water masses. Let's talk a little bit about the distribution of temperature in the world's oceans. As with salinity, I'm showing you here is the decadal average temperature in surface waters from 1955 to 2017 from World Ocean Atlas Climatology. Right away, a couple things jump off the page. Higher temperature in the tropics and the mid-latitudes than up at the poles. Another is a much, much wider range in temperatures in surface waters than we see in salinity. Again, that makes sense from what we already know looking at the equation of state for seawater. Although each unit temperature has a lesser effect on density than each unit change in salinity, temperature can vary over a wide range. In fact, that wide range is as low as -2 degrees Celsius, which is the freezing point for seawater, to in excess of 30 degrees Celsius. Now remember, this is surface waters. In the deeper waters of the ocean, ocean temperatures are low. I like to say this is a great piece of oceanographic trivia. When somebody asks you, what's the average temperature of deep waters in the ocean, you can just look smart and say 2 to 4 degrees Celsius, and you're pretty close. On average, ocean temperatures are about 3.5 degrees Celsius. But at the surface, they can change a lot. So we have to look at the why surface ocean temperatures change. Well, any discussion of surface ocean temperatures starts with the heat source, which is going to be energy from the sun. So what you're looking at right now is a monthly plot of annual net radiation. So the net radiation reaching the surface of the Earth from the sun. Now all you got to do is blur your eyes. You can see the seasonal change between the northern and southern hemisphere, but you'll note right by the tropics and the mid-latitudes, there's a lot more orange than there is in the poles. So that tells us we have a net positive or surplus of net radiation around the tropics and the mid-latitudes on Earth, and we have a net deficit of radiation at the poles. This is what's going to drive heat exchange in the oceans, and this is what's going to drive a change in temperature in the surface waters of our oceans. How do we calculate the change in temperature of the surface ocean due to heat transfer from the atmosphere into the ocean or vice versa? Well, we can do that using some bulk approximations. I'm not going to beleaguer you with math right here. I'm just going to try to broadly explain the math. So what you're looking at right here is a simple bulk box model for the transfer of heat across the ocean surface. That's exchange of heat with the ocean surface and the atmosphere. So this term, Q sub T, is net heat flux across the sea surface. In other words, between the ocean surface and the atmosphere. We can look at net heat flux, and it's going to be equal to the heat flux across the sea surface from incoming solar radiation minus the heat flux across the sea surface from outgoing long wave or infrared radiation, minus the heat flux across the sea surface due to evaporation, that's going to be latent heat exchange, minus the heat flux across the sea surface due to a temperature difference between the air and the sea. That's sensible heat transfer. Now there's also another term when we're looking at box models, and that's heat flux due to advection or fluid motion. Think of that as heat coming in or out from the sides due to the flow of water, or the movement of water by currents. In most cases, for simple approximations, let's just assume that's equal to 0. In other words, we're not going to add in currents at this point. Now the reason I show you this, because if we can calculate net heat flux across the sea surface in watts per meter squared, and multiply that over a time period times an area of the oceans, this gives us energy. Now, energy is going to be equal to the mass of water times the specific heat capacity of water times the change in temperature of that water mass over a depth. So what you can see right here is if we can calculate energy, we can calculate change in temperature. How do we do that? Well, this is the math that I would use in a bulk approximation of net heat transfer across the ocean surface with the atmosphere. And this is how I would calculate each of the individual terms. I'm not going to beleaguer you with going through this calculation, but instead let's look right down here at the final product. If I can calculate that net heat transport across the air-sea interface over time, I can set that equal to the depth integrated value of the specific heat capacity of seawater times its density times its change in temperature, solve for change in temperature of a given depth of water. Now this is a bulk approximation, but what it tells us pretty elegantly is if my net heat transfer across the air-sea interface is less than 0, temperature goes down. If it's greater than 0, temperature goes up. Now we're ready to look at an ocean water column temperature profile. Again, this is a typical generalized profile. One will find different profiles based on the conditions that one sees in the water column. So as with salinity, the surface mix layer typically extends to a depth of about 200 meters, and it's characterized by uniform temperatures within the mix layer. A zone where temperature generally decreases with depth is called a thermocline. Now, a permanent thermocline exists from about 200 to approximately 1,000 meters in the deep ocean. Why is this the case? Well, it's because temperatures in bottom waters of the deep ocean are very stable down here, and they're typically between 2 to 4 degrees Celsius. So in the deep ocean, anywhere you go, you're probably going to find that waters below 1,000 meters, or especially below 1,500 meters, are going to be stable between 2 to 4 degrees Celsius, and we're going to see a thermocline that terminates typically around 800 to 1,000 meters. We call this the base of the main thermocline. Now, one does find other thermoclines in the ocean water column that are effect of seasonal changes in heat exchange from the surface ocean to the atmosphere. Kind of makes sense. Imagine heat exchange of an ocean water column in Maryland, where we're going to be for the Project Ocean course that's in the mid-latitudes. In the summertime, you're going to have higher surface water temperatures, and in the wintertime, you're going to have lower. That's going to change the thermocline in that very surface water, but below that, it's really this deep water heat sink that's going to drive the shape of the permanent thermocline. So one can see different thermoclines. This permanent thermocline is what one would expect to find in most areas of the deep ocean. Now, you've heard me use this term deep water. I'm going to define that for you here in a second. Well, I might as well do it now. When you hear me use the word deep water, I'm really talking about waters deeper than 1,500 meters in the world's ocean. I'll explain that here in a second. But looking at temperature, one thing really jumps off the page at you is that That is a big difference between a surface temperature about 15 degrees and a bottom temperature about 2 degrees. So that provides a really steep ocean thermal gradient. It tells us the oceans can store a lot of heat. And we'll see this is what makes the oceans very important as regulatory mechanisms for global climate. If one wants to find where heat's going, look at the ocean. The oceans are just heat sinks for temperature. Putting it all together, again, this is a World Ocean Atlas climatology, a decadal average from 1955 to 2017 showing global surface water density. Look at the range from about 22 kilograms per meter cube to an excessive 28 kilograms per meter cube. Not surprising, we find our lowest densities here in the tropics, where we also find our highest temperatures. We tend to find our highest densities down near our colder waters, although you can see some variability, which we'll talk about in ocean circulation, like right up here in the North Atlantic, the Arctic Ocean, which remember is going to be preferentially more fresh. But looking at this, it's pretty obvious that temperature is doing a large role of controlling density structure. Now, lines adjoining areas of equal density are what we call isopycnals. I want you to tuck that term into your memory. We'll define that more when we start to look at density-driven circulation when we're in person in Chestertown during the Project Ocean course. As with salinity and temperature, let's take a look at an ocean water column density profile. Again, this is a generalized typical profile one would expect. You can find variation on this based on local conditions. Before we jump into discussing this profile, here's where I'll formally define some of these depth-specific divisions within a ocean water column. We've already learned about this surface mix layer, typically defined as waters from 0 to 200 meters, characterized by relatively uniform properties within that layer due to mixing at the surface by wind and waves. Below that, from 200 meters to 1500 meters, we call these intermediate waters. And from 1500 meters to the bottom are called deep waters. Now, bottom water, you may also hear that term, is just deep water that's in contact with the seafloor. I show you these definitions right now because more and more you're going to start to hear me use this terminology, especially when we get into talking about tracing water mass in density-driven circulation. But going back to density profile, remember that term Klein? Well, zones where density increases or decreases with depth is called a pycnocline. Now, in the deep ocean, the depth of the main pycnocline, or the base of the main pycnocline, tends to be coincident with the main thermocline. We've already talked about the reason why, and the reason why is because although temperature has a lesser effect on density for each unit change than salinity does, temperature varies a much larger range than salinity does. Therefore, the thermocline and the pycnocline are typically coincident. And all you got to do is look here. Remember that the base of the main thermocline is typically somewhere between about 800 meters and 1,000 meters. And right there you can see the end of the permanent or main pycnocline. Now notice also that here in deeper waters, once you get below a lot of these effects of temperature and salinity in surface waters, density tends to continue to increase slightly, and that's just due to the effects of pressure alone. Now, why is this so important to look at this water column density profile? Well, if we look at the combined effects of temperature, salinity, and pressure in a static ocean water column, that is, we'll see that the static ocean water column is layered according to density. In other words, here we can see this is less dense than the water down here. Now, that's important because a stratified or layer water column is more stable. In other words, if I have less dense water on top of more dense water, that is a very stable system. For those of you who have studied the atmosphere, you see the opposite in the atmosphere down in the tropopause. In other words, you have a less dense air mass underneath a more dense air mass that creates circulation in the lower atmosphere. The ocean is pretty darn stable. So ocean stability generally increases with depth as density and stratification increase. That stratification and layering inhibits mixing because energy is required to break down stratification. So the more stratified a water column, the more stable it is and the harder it is to mix. Now we'll see when we get into wind-driven circulation, the mixing of an ocean water column comes from the surface and decreases rapidly with depth. And this tells us that most of the action we're going to see in the ocean water column is going to happen in the surface because a stratified or stable ocean water column is going to resist any mixing, and there's just not a lot of mechanisms to mix deeper waters. This is why it's really important to understand water column structure in order to understand physical circulation. We will get to this when we talk about wind-driven circulation and density-driven circulation. Just to drive my point home, I'm going to end this remote lesson with some math. In other words, I'm going to show you just a mathematical ratio that compares stratification or layering versus mixing. We're going to do this so we can get just a mathematical concept of stability. So what I'm showing you right here is something called the gradient Richardson number. Don't worry about solving this or deriving it. All I want you to do is kind of take a look at it. And I'm going to show you some key terms right here. The first is this term in the numerator, change in density with change in Z. Remember, Z is depth, increasing negative in the oceans. The other term down here is going to be change in flow velocity or velocity shear in the horizontal direction. I'm only going to look at the X direction. I could also do this in Y. And that change in flow or shear with depth, that is mixing. So this tells us that the gradient Richardson number is going to be a ratio between stratification and mixing. If that value is greater than 0 stratification winds, that means that ocean water column is very stable. If it's less than 0, it's unstable, and that means that ocean water column wants to mix. So we can compare properties within an ocean water column to look at how stable it is. So really what the gradient Richardson number tells us, it's the ratio of the gradient of stabilizing forces of density stratification to the destabilizing influences of velocity shear throughout the water column. This understanding is going to get us to wind-driven circulation. So relative stability of the water column is simply a ratio of the change in density with depth versus the change in the mixing with depth. So understanding this really is the key to understanding physical circulation and the movement of water in the deep ocean. We covered a lot. So once again, here's your learning objectives. Please review these against your Project Ocean understandings. Now this is a time to ask questions. You probably have a lot of questions. I don't expect you to be experts after this remote lesson. This is the basis that will allow us to have some great discussions and to learn together when we see each other in person in the Project Ocean in-person course in Chestertown. Thank you again. Send your questions to me, or you can post them in the discussion board on D2L.